Hello everyone, my name is Emily J. Hewitt, and I'll be presenting my Physics 2212 Lab 3 circuits. The goals of this lab were to predict and measure the behavior of circuits in series using the principles of current conservation and energy conservation. We also wanted to compare the behaviors of resistors and capacitors in RC circuits. Overall, our measured value agreed very closely with our predicted values. We also observed that increasing the resistance increased the amount of time required for the capacitor to charge and discharge. Our model for the experiment was the Colorado PhET circuit construction kit simulation. Our system we analyzed with the circuit itself while everything else was the surroundings. There are four main principles we used throughout the experiment. The node rule states that the current entering a junction equals the current leaving it. Second was Ohm's law, which relates voltage, current, and resistance through the equation V equals IR. Third was the loop rule, which states that the sum of all voltage changes around a closed loop must equal zero, demonstrating conservation of energy. And finally, for the RC circuit, we used the equation below, which allowed us to demonstrate the RC time constant from the slope of our graph. Our first task was to predict the current measured by both ammeters. Since the resistors were connected in series, we added them together to find the total resistance. 47 ohms plus 100 ohms gave us the total resistance of 147 ohms. Using Ohm's law with the 3-volt battery pack, we calculated the current to be approximately 20 milliamps. Because of this series is a circuit, the same current flows through every component, so we predicted both the ammeters would measure the same current. Next, we reversed the orientation of one of the ammeters. The magnitude of the current did not change because the reversing the meter does not affect the circuit itself. The only difference is that the meter would display a negative current since the conventional current is entering the meter through the opposite terminal. We then replaced one of the ammeters with a voltmeter. The voltmeter had an extremely large resistance, so placing it in series effectively opens the circuit. As a result, the current drops to essentially 0 amps because the electrons can no longer flow. The voltmeter measures approximately 3 volts because the entire battery voltage appears across the open portion of the circuit. Next, we measured the voltage across different sections of the circuit. Using the loop rule, we expected the battery to provide a positive 3-volt increase in the potential. The 47 ohm resistor produced a large voltage drop of approximately negative 0.96 volts, while the 100 ohm resistor produced a voltage drop of about negative 2.04 volts. When all these voltage results were added together, the total was approximately 0 volts, confirming the conservation of energy. This graph shows how electric potential changes as you move around the circuit. The potential increases across the battery because energy is added to the charges. It then stays nearly constant through the connecting wires but decreasing across each resistor. Notice that the larger voltage drop occurs across the 100 ohm resistor because it has the greater resistance. Overall, the graph clearly illustrates Kirchhoff's loop rule since the potential returns to its original value after completing one full loop. We then replaced the voltmeter with an ammeter and connected it in parallel with 100 ohm resistor. Because the ammeter has very low resistance, it creates a short circuit around the resistor. Most of the current flows through the ammeter instead of the resistor, reducing the circuit's total resistance from 147 ohms to approximately 47 ohms. As a result, the current in the circuit is increased significantly. Using our measured voltages and current, we calculated the resistance of each component using Ohm's law. The 47 ohm resistor measured about 48 ohms, while the 100 ohm resistor measured about 102 ohms. The wires and ideal ammeter both had essentially zero resistance. These values matched the expected values, indicating our measurements were accurate. The second portion of the lab focused on RC circuits. When the battery was connected, the capacitor charged. Initially, the bulb was bright because the current was high. As the capacitor accumulated charge, the current gradually decreased, causing the bulb to dim. When the battery was removed and the capacitor was discharged through the bulb lit briefly again and before fading as the stored energy was released. For the final experiment, we used a 9-volt battery, a 200 millifarad capacitor, and a 30-ohm bulb. The theoretical RC time constant was calculated by multiplying the resistance and capacitance, giving it 6 seconds. Next, we plotted the natural logarithm of the normalized voltage versus time. Because the slope of this graph equals negative 1 over RC, we used the measured slope to calculate the experimental RC value of approximately 6.78 seconds. This was reasonably close to the theoretical value, showing a good agreement between our experimental and mathematical model. Our primary assumption was that the simulation accurately represented the behavior of real electrical circuits. The largest sources of error came from human reaction time when starting and stopping the timer, along with small calculation and rounding errors. Despite these limitations, the experimental results matched our predictions very well, supporting both Ohm's law and the conservation laws using the lab. The first question asked what would happen if we used a real battery and capacitor with no resistor. According to the ideal model, if the resistance is 0, then the time constant RC is also 0. This predicts that the capacitor would charge instantly. However, this doesn't happen in real life because batteries, wires, and capacitors all have small internal resistances. This unavoidable resistances limit the current, so the capacitor would take a finite amount of time to charge. The second question asks about using a real ammeter instead of an ideal one. The ideal ammeter has a 0 resistance and does not affect the current. A real ammeter has a small internal resistance, so inserting it into a circuit slightly increases the total resistance. This causes the current to be slightly lower than the ideal value and introduces a small amount of measurement error, although the effect is usually very small. Overall, this experiment demonstrated how the conservation of conservation of energy, Ohm's law, and the RC equation accurately describes the model